In this video, we're going to look at how to get meaningful information from a fast Fourier transform, from an FFT. And I want to clear up what I see as a lot of confusion on how to scale an FFT in a way that provides an understanding of the properties of the time domain signal. Specifically, I want to cover how we go from an FFT to amplitude, and to power spectral density. And I want to talk about why we may choose one representation over another and the scenarios in which they are valid. I think this will be useful, so I hope you stick around for it. I'm Brian, and welcome to a MATLAB Tech Talk. If you don't know what an FFT is, then I recommend watching my video on it that I've linked to below. But for right now, all that you really need to know is that when you take an FFT of a signal, it returns a vector of complex numbers. And here I'm just plotting the real and imaginary parts of an FFT for time signal xn. And these numbers represent the phase and the magnitude of the frequencies that exist within x sub n. And in that video, we covered how in some cases we aren't concerned with phase, so we just look at the magnitude by taking the absolute value of the FFT. And then, when dealing with real time signals, the magnitude of the FFT is duplicated between the positive and the negative frequencies. And since the information is the exact same, we can choose to only look at the positive frequencies, a so-called one-sided FFT. And this is where we left that video, with a one-sided plot of magnitude versus frequency. Now, how can we use this information to understand something about the time signal? And when it comes to spectral analysis, the question you have to start with is, why are you doing it? What are you hoping to learn by analyzing a signal in the frequency domain? And the reason that this is an important question is because the tool that you use to do your spectral analysis depends on your goal. And in the case of this video, how you manipulate the FFT depends on your goal. For example, if all you want to know is where frequency content exists in the signal relative to each other, then this magnitude plot is sufficient. I mean, I can tell that there is a strong frequency component at 110 Hertz, and there is a weaker but still obvious component at 100 Hertz. And this level of analysis might be good for figuring out, if there's a 60 Hertz noise in a signal, or maybe what the natural frequency is of a structure that's vibrating. So it's pretty cool that you can get that information from the magnitude. But the downside of this plot is that this value on the y-axis isn't a quantity that relates to some physical property of the time signal. So what if you do want to know something quantitative about the signal? Say you want to know the amplitude of a sine wave at a particular frequency. Well, I'm going to spoil it for you. This is how you do it. You take the absolute value of the FFT and then divide by capital N, which is the total number of samples in the signal. This produces amplitude, but it's split, with half of the amplitude being captured in the positive frequencies and the other half in the negative frequencies. And so if we just want to look at a one-sided spectrum, we ignore the negative frequencies and double the values for every positive frequency, except for the DC term, which is 0 Hertz, and the Nyquist frequency. And we can go over to MATLAB and see that this works. It actually returns the amplitude of a sine wave. I have a time signal with two sine waves, with amplitudes 1 and 4. And then I take the absolute value of the FFT, divide by the number of samples, and then look at just one side and double it, except for the DC and Nyquist. And when I plot this spectrum, the y-axis now shows amplitudes of 1 and 4. So, perfect. But the question might be why are we dividing by n? I mean, why does this work in the first place? Well, let's quickly walk through an explanation. Okay, so the FFT is mathematically equivalent to the discrete Fourier transform, which says that we start with a time signal, xn, multiply it by a correlating signal, which is this exponential here, and then sum over all of the samples. And this produces the frequency domain coefficients xk. Also, e raised to an imaginary number is just a function of cosine and sine. Alright, so now let's say that the time signal is just a sine wave with amplitude a. And it doesn't matter what frequency it's at, so I'm just going to put a dot in here. And if we plug this into the DFT, we get that xk is equal to the amplitude a times the summation over all of the samples of sine times cosine minus I times sine squared. And sine times cosine produces another sinusoid, and so the summation over one period is 0. It cancels each other out. So no matter how long the signal is, the summation will always be close to 0, and therefore this first component doesn't contribute much to the summation. Sine squared, on the other hand, looks like this, like a sinusoid that goes between 0 and 1. And since this is discrete, we're sampling it in times. Now, the more samples we have, the larger this summation will be. However, if we add up all of the samples and then divide by the number of samples, this will give us the average height of the sine squared function, right? I mean, if you add up 10 numbers and divide by 10, you get the average value. Well, the average value for sine squared is 1/2. So if we go back to the above equation, we can divide xk by n, and now this whole summation is 0 for the first component still, but it's 1/2 I for the second component since it's just the average height of sine squared. Now we're taking the absolute value of x of k, which gives us the magnitude of the FFT, and that is equal to half the amplitude. And again, the reason that it's in half here is because the amplitude is split between the positive and negative frequencies. But if we're just looking at a one-sided FFT, then, we're multiplying this by 2, and we're left with amplitude. Now, I just want to note that if our original time signal had a phase shift to it, this all still works out mathematically. I just did a zero-phase sinusoid to make it easier to follow. But I think overall this is pretty cool, that we can find the amplitude of a sinusoid simply by taking the FFT and scaling it. Alright, so that's amplitude, but what if we want to know power at a particular frequency? Well, the average power of a sinusoid is just its amplitude squared over 2. And since we know that the absolute value of the FFT divided by n gives us the amplitude over 2, then the easiest thing we can do is just square that value. And this is the two-sided power spectrum since the power is split between negative and positive frequencies. So to get the one-sided power spectrum, we multiply it by 2. And this is how we go from the FFT to the one-sided power spectrum. So let's go back over to MATLAB and see how we can implement this. This, by the way, is the same script as before, so we're working with the same two sine wave signal. And I'm just going to scroll down past amplitude and get to the power section. So here, I'm taking the absolute value of the FFT, then squaring it, and dividing by n squared. And then to get a one-sided power spectrum, we ignore the negative frequencies and double the positive frequencies. Again, except for DC and Nyquist. Now, the plot looks like this, with powers of 1/2 and 8, which correspond to the amplitudes 1 and 4, respectively. So it all works out nicely. But often, we like to look at power in decibels, so let me do that here real quick with the pow to dB function, and then rerun this script. And this is the one-sided power spectrum that I created, and it took several lines of code. But you can, type all of this out each time you want to get to the power spectrum, or you can just get the exact same result with the periodogram function. And there's many different ways to create a periodogram, but here I'm running it with a rectangular window, an FFT, which is the length of the entire signal, and then setting it to return the power spectrum instead of power density. These are the parameters that exactly copy what we just coded above. And you're going to have to take my word for it here, but these two plots are identical. So there we go, right? To get one-sided amplitude, we take 2 times the absolute value of the FFT and divide by n, and to get power, we take 2 times the absolute value of the FFT squared and divide by n squared. That's pretty easy, right? Well, kind of. We have to be really careful here, because these results are only true if there are 3 very important things. One is that we're using a rectangular window and not some other window like Hamming or Blackman. 2, the time signal is stationary. And 3, we're dealing with time signals that produce discrete frequency power spectra and not a continuous spectrum. So let me go through each of these and explain why they're important for these equations to hold. And we're going to start with the rectangular window. When we take the FFT of a time signal, it necessarily must be finite. There is a start time and an end time. and therefore we're really only looking at a small subset of the total possible infinite signal. And from this subset, we're trying to understand the signal properties. And this subset of data is called a window since we're only looking at a portion and the rest is obscured from view. Now, the window could be long, or it could be short, or we could look at a different part of the signal altogether, but no matter what, we're always just looking at a subset. Now, what I've drawn here is a rectangular window, and this means that each sample in the window is unmodified. That is, we multiply everything inside the window by 1, and then 0 for everything outside of the window. And this makes sense, right? I mean, why would you want to change your signal if you're trying to find out the properties of that signal? Well, one reason is for spectral leakage. And one way that spectral leakage occurs is when the period of a time signal frequency is not an integer multiple of the window length. In these cases, cutting a period short like this spreads that signal energy out into neighboring frequency bins, since that summation that we talked about earlier doesn't get fully canceled out by having a complete period. And one way to mitigate this is to just use a longer time series, because that leftover period gets averaged across a longer time span. But if that isn't possible, then another way is to just apply a non-rectangular window to your data, something like a Hamming window that attenuates the signal near the edges and reduces the effect of that partial period. Now, this reduces the spectral leakage, but it also comes at a cost of lower resolution. And I'm not going to cover different windows much in this video. I just want you to be aware that you might not always be dealing with a rectangular window. And as you might expect, if you attenuate the signal near the edges, you are of course affecting the average amplitude and the average power within that window. Therefore, the equations that we derived for amplitude and power are only valid for rectangular windows. And there are ways to account for the effects of the window when looking at power, which I'm not going to cover in this video, but if we go back to MATLAB and the periodogram function, we can see that it does handle the effects of the window, because both Hamming and rectangular windows produce the correct power for the 110 Hz frequency that I'm showing here. Alright, for the second requirement, the time series must be stationary. And this just means that the signal, from a statistical standpoint, doesn't change over time. The mean and the variance of the signal are the same regardless of where you look. And here's a way to understand why it's a requirement. Remember back when we were deriving the amplitude, we divided by n because we were looking for an average amplitude. And we sort of had an assumption that the amplitude is relatively constant across the window, right? I mean, take for example this signal. It's a single frequency, but the power is changing throughout the window. If we calculate the power for this frequency, it will give us an average across the window, but it won't provide any indication that the power is changing. Now, a worst case scenario of this is if there is a very short-term, high-powered event that is just averaged across a long window, potentially causing it to be lost in the noise. Alright, so we know that we want a rectangular window, and we want the signal within that window to be stationary. Now for the third requirement, we need the signal to have discrete spectra. And why this is required is really important. To explain why, let's go back over to MATLAB. Here I have a time signal with two sine waves, one at 100 Hz and one at 110 Hz. And then I'm taking the FFT and then scaling it for the power spectrum. Now, what I'm plotting here is the true power for the two sine waves, and that's the red and yellow stems. And I'm also plotting the power spectrum for the signal, which is the blue curve. And notice how these peaks for the blue curve aren't perfectly sharp, but they're spread out a little bit. And this comes from spectral leakage that occurs because we're using that finite window. But the important thing is that the peak of the power spectrum is at 8. So even with this spread, we're getting an accurate measurement of the power at these frequencies. Now, let me hide the code here so that we can focus on this graph. And watch as I move the frequency of the second sine wave closer to the first. At some point, their spectra start to interfere with each other. And then, when they're too close, they merge into a single peak. Now, the value of the y-axis isn't reporting an accurate power at that frequency. In fact, we can't say much of anything about the power of each individual sinusoid. What's being reported is some combination of the two frequencies that are just too close to each other to separate out. Now, this is just two discrete sine waves, but imagine the case of broadband signals where the frequency spectrum is continuous. In this plot, I'm showing 50 sinusoids between 100 and 100.5 Hertz, and each of them contribute a very small amount of power. But if I zoom out, we can see that the power spectrum for the time signal is much higher because they all contribute a little bit to that total. So hopefully you can see that this peak doesn't represent a power at a particular frequency, but the power of all of the frequencies that contribute to it. So in some way, it represents power density. This area is much more dense than these areas are, and we can tell that from the peak. And we can normalize this plot by dividing it by some frequency bandwidth, specifically the equivalent noise bandwidth, which is, in some way, the width of the frequencies that contribute to a particular sample in the power spectrum, and it is a function of the window itself. A finite length window will necessarily blend the power of nearby frequencies together, like we saw, and we can see how this blending occurs by looking at the power spectrum of the window itself. For a rectangular window of length 128 and sampled at 1000 Hertz, this is its power spectrum. And I've shifted the negative frequencies to be over on the left so that we get a better sense of what this curve looks like. And notice that the window has a maximum power of 1 right at 0 Hertz. So the way that we can interpret this is that this window will pass through the power for the frequency that is being sampled unmodified. It's multiplying it by 1. So, in this way we can accurately get the power from a single sine wave. However, along with that value, this window will also add in the power at all of these other delta frequencies, attenuated by the amount given by the curve. The longer the window, the steeper the curve, which means that a longer window will have fewer contributions from nearby frequencies than a shorter window does. Alright, so each sample in the spectrum is the summation of the attenuated power from all of these nearby frequencies. So we might think that the bandwidth we're interested in is, however far out this tail goes, since all of those frequencies are included in some way. But as we can see, these far away frequencies don't contribute very much. We really only want to consider the frequencies that have the most impact. And the way we find that is to approximate this curve using a rectangle with height equal to the peak and whose area is equal to the total power. So the area under the blue curve is equal to the area under the red rectangle. And the width of this rectangle is the equivalent noise bandwidth. And under this assumption, we can say that this is the range of frequencies that contribute to each sample in the spectrum. And so to get power spectral density, we divide the power spectrum by the equivalent noise bandwidth. And we know power spectrum, it's the absolute value of the FFT squared divided by n squared. And this is the equation for the equivalent noise bandwidth for an arbitrary window. And I'll leave a link below to a derivation for it, but the way that we read this is that we square each of the terms in the window, and then sum them all up and multiply that by the sample rate, and then divide by the sum of the window terms, which is then squared. And so for a rectangular window, each of the n terms have a value of 1. And so this just becomes fs times n over n squared, or fs divided by n. And now when we divide the power spectrum by this, the n's cancel out and we're left with 1 over fs times n times the absolute value of the FFT squared. And this is the scaling for power spectral density using a rectangular window. And for the last time in this video, let's go back to the MATLAB script and see it in action. And you know what's going on at this point, right? We're just taking the absolute value of the FFT, squaring it, and dividing by fs times n, and voila, the power spectral density. And instead of typing all of this out again, we can use the periodogram function to generate the PSD. And the nice thing about this function is that it's really easy to change the output to power, or to change the window and, see the results really quickly. Now, if you want to play around with this script a little bit, I've left a link to it below. But I hope that this whole thing has cleared up some confusion about the FFT and power. And the thing to remember is that if your signal is made up of a few dominant sine waves, then you can look at the power spectrum to get the power in those frequencies. However, if there are broadband signals, then it probably makes more sense to look at the PSD instead, since that returns the power per frequency band. And mathematically, you can take the PSD of a single sine wave, or the power spectrum of wideband signals, and you're going to get a plot. But the trouble comes when you try to tie those plots back to some physical property in the time domain, because they just won't make much sense. And this is why you have to know what you're trying to accomplish and what kind of signal you're looking at in order to choose the correct tool. All right, so that's where I'm going to leave this video. Don't forget to subscribe to this channel so you don't miss any future videos. Also, you can find all of the Tech Talk videos across many different topics nicely organized at MathWorks.com. And if you liked this video, then you might be interested to learn about the fast Fourier transform in our video on the FFT and the DFT. All right, thanks for watching, and I'll see you next time.